So our next problem is gate code number 834, sum of distances in tree. So there's an undirected connected tree with n nodes labeled from 0 to n minus 1 and n minus 1 edges. You're given an integer n and the array edges where edges of phi is equal to ai comma pi, which indicates that there's an edge between nodes ai and bi in tree. Now we need to return an array answer of length n, where answer of I is the sum of distances between the ith node in the tree and all the other nodes. So for example, answer of 0 would be the sum of distances between the 0th node in the tree and all other nodes. So sum of distances would be basically, in this example, let's say we have n is equal to 6, right? And edges are this, so we connect to form this tree or this graph. So the tree is shown. We can see that distance of 0 comma 1, basically first answer of I answer is going to be something like this. So we have 0 1 2 3 4 and 5. All these nodes would be like this, and basically here we are storing distance of the sum of the distances for 0 with all the other nodes, which is equal to 8. So that's that. And from 1 we basically need to calculate, similarly from 1 we need to calculate all the other distances to to all the other nodes. So let me just show you from scratch how you calculate this. So firstly, for this index, which is answer of 0, we calculate distance of 0 with all the other nodes and then sum these up. So distance of 0 from 1 would be 1, then distance of 0 with 2 is 1, distance of 0 with 3 is 2 because there are 2 edges between that. Then similarly for 4 and 5 we add 2 more. So you see that this is 2 plus 6, that is 8. So that is how you get for 0 node, we have the sum of the distances to all other nodes from the node 0 as 8. So that's answer of 0. Now for answer of 1, let me show you. From 1 to 0 we have the value as 1, then from 1 to 2 we have the distance as 2, then from 1 to 3 we have distance as 3. Similarly for 4 and 5, because there are 3 edges for each, right? So that basically becomes 3 times 4, that is 12. And you can see distance of the sum of the distances from node 1 to all the other nodes would be 12. Similarly for all the other nodes, you can calculate and see that these are the values. So we basically have this problem at hand, and for basically the base cases, you can see uh, sum would be 0 because there are no other edges, so obviously the sum would be 0. And for this case, you have the sum as basically the distance of 1 with 0 is 1, and similarly vice versa, distance of 0 from 1 is 1. So that is why we have 1 comma 1. So that's the basic explanation of the problem, and now we have to move on to the implementation, right? So let me show you how we're going to be solving this problem. So firstly, you can just imagine that since you are traversing the tree, right, you need to traverse the tree. So there are two options: either you can apply DFS or BFS. So DFS is depth first search, or BFS is breadth first search. So we're going to be applying DFS first to compute two things, right? There are two things that we are going to compute. First is the distance sum from node 0 to all the others, that will be stored in a result uh, vector. And secondly, we are performing DFS to compute the number of nodes in each subtree that is stored in each child. So distance sum from node 0 means that we're going to sum up all the distances to the other nodes from the node 0. And secondly, the number of nodes in each subtree is basically, for each subtree we're going to calculate the children plus the number of nodes in those subtrees, that is those children, right? So that is stored in the child vector. uh, right. So now what we're going to do is basically, this is our main function, that is sum of distances in tree. So what we have basically done here is that we're given n and the edges vector. So we create the adjacency list for the undirected graph. So that is basically the simple initialization. After that, what we have done is that we declare a result integer variable to store the answer for node 0, that is the sum of distances to all the nodes from node 0, that would be stored in result, that is equal to 8 for this case. So that would basically be stored in result. Now we're declaring two vectors of int type, that is child and visited. So child basically both of these are initialized with 0. The child of I would be basically the number of nodes in subtree rooted at I. So for example, child of 2 would mean that the number of nodes in the subtree rooted at 2. So that basically includes 2 and the number of nodes that are within or below this. So that is in the subtree. So that is equal to child of 2 is equal to 4, right? Similarly, if you were to say for 1, child of 1 would be 1. Child of 3, since these are all leaf nodes, would be equal to 1. This child of 4 is equal to 1. Child of 5 is equal to 1. And child of 0 would be equal to the sum of all these. So the subtree, the left subtree, the right subtree, and uh, the the node rooted at I itself, right? So that's child of I. And visited is basically for performing DFS, the first reversal on the root. Right. So first step is to perform the DFS, post order DFS, to compute the result for node 0 and the subtree sizes. So we get perform DFS to get the answer, that is sum of the distances from node 0 along with the subtree sizes for each of these. Right. So let's go over to the DFS function, and then we'll come over to this BFS function. So the DFS now function, it takes the node we are at, which is the ith node. So for example, we are standing here, so that is the ith node. the adjacency list, the child vector, the visited vector, the result, and the level. So we first mark the node as visited because we are standing at this current node and we mark it as visited. Then we add the result to the, sorry, add the level value to the result, that is add distance from root to the current node. So we are basically summing up the distance. DFS will basically calculate and give us the sum from node 0 to all others. So firstly, we are calculating the distance and then we are summing it up. The DFS calls would sum the remaining ones. Firstly, we are just adding the level, right? Now we're initializing number of nodes in the subtree with children, and children is equal to 0. And then we're visiting for each neighbor in the adjacency list of node. If the neighbor has not yet been visited, for example, if 2 has not yet been visited, then we visit it and we add the value recursively to children, because that would basically get us our value for each child in the subtree. So that is how we adding it, and we increase the level by 1. All the other parameters remain the same. Then we return child of node is equal to children plus 1, because total nodes in the subtree are all the children of this, for example, for 0, all the children for the node 0 and the node itself, that would be stored in the child of node, right? So that I had explained to you earlier. So this completes our DFS function. So this was the function to just compute the sum of distances from node 0 to all other nodes and the number of nodes in each of the subtree. So we have performed DFS for that. And now we're moving on to BFS to compute the result for all nodes. So basically in answer, we have computed this value, but we need the value for all the other nodes. So that is why we need all these for calculating all these other values. We're going to carry out BFS to compute the answer for them. So again, we initialize a visited vector for the second traversal and answer vector, right? And in answer, we are basically pushing the first value that we have achieved, that is the sum of distances from node 0. So that we have initialized. Where is it? Let me show you. Wait a second. Yeah, this is the value. So for BFS, we have to initialize a queue. So I've declared it in a pair of int, int type. So that would be storing, the queue would be storing node and the parent of the node, right? So to keep a track of the node along with its parent. So we put pushing 0, 0. So vis1 of 0 is equal to 1. That means that we've already visited the node 0, right? So we mark it as 1. So the root node 0 has been visited already. So we have marked it. Now we're moving on to the while loop. So while the queue is not empty, the node and the parent, we first get them and pop the queue. So we've received the node and the parent. Now we check if the node is equal to 0. Yeah, there is a check that if the node is equal to 0, we have already computed the value for this. So we store the answer of the answer, that is the result, that is the value 8 in answer of 0. So the index 0 carries the value, so that is stored here since we have already computed it. So for node 0, the work is done. Now we're going over to all the other nodes. So if the node is not 0, that means it is any of the other nodes. We have to compute for this. So when we move our root from one node to its connected node, one part of nodes gets closer and the other part gets further. So we need to use the parent result to compute this node's result. So we need to use the parent result to compute this node's result. So parent value we get from answer of parent, and we basically distribute this into two subtrees. So we get upper nodes as n minus child of node, that is nodes not falling in the subtree of this nodes. So if we move the root, in simpler words, if we move the root from a parent to a node. So for this example, if we move the parent from node 0 to 2, so here parent is 0 and the node is 2, then the subtree of node, that is 2, the subtree of node moves 1 closer. Now the subtree has moved closer to the child nodes, that is 3, 4 and 5, right? So the child node, it has moved closer, and all the other nodes, that is 1 and the other nodes, if there were any, they have moved one edge further away from this node, that is 2, right? So all the nodes move one further. So for that, we have basically made these two values, that is n minus child of node, which is the other nodes, that is the node 1 in this example. N minus child of node would basically help us move this node one further away, right? For 0, we had this node at distance 1, but for 2, now since we have moved to the child node, the subtree would basically have the distances closer by 1, and all the other nodes that are not in the subtree would be having an additional distance of 2 for like 1. For the node 1, we have additional distance, right? Because if we have node 1, we have moved one node down in the tree. So that's basically the explanation. And you can see that we are storing answer of node as the parent value minus the child node. So this value minus the child node plus the upper nodes. So all the upper nodes, that is this nodes not falling in the subtree. Child of node is this. Child of node is this value, right? So basically 1 plus 2 plus 3, and upper nodes are basically this value, and the parent value is this, right? So that's the mathematical part, and this was the main part of this problem. This was the most trickiest part. Other than that, we just basically, for completing our BFS, we visit all the neighbors for this node. So we're visiting all the other neighbors, and we check if the neighbors have not yet been visited. Then we push them into the queue, push basically the neighbor and the node. So neighbor is basically now the current node, and the previous node has become the parent. And then we mark the neighbor as visited. Finally, when we come out of the loop, this runs. So all this runs and all the nodes are covered. Right. Once all the nodes are covered, we return our answer, and the answer would contain all these values that have been calculated, which are basically the sum of the distances of each node from all the other nodes, which are stored in this array. And let me just submit and show you whether it's getting accepted or not. So yes, it has been accepted, and yeah, that's it for the video. Thank you guys for watching.